All right, so let's start the second part, not the demo, but yeah, the second part related to multi-threading. And now let's talk a little bit how that relates to multi-threading. First of all, specification says that there should be particular concurrency guarantees. Like every solution, especially reactive streams, are assumed to be run in concurrent environment. So they say that particular method should have particular synchronization like this, which means so all on next, on complete, or on error invocation on your subscriber should be properly serialized. What does it mean? How do you interpret this word serialized? Your idea? Just yes, something like this. But in general, serialized mean that in reactive streams, every signal should be invoked serially or one by one without any concurrency. So it means that you have to take a proper care to prevent any simultaneous invocation of to on next. Why it's important? Just imagine that you are building a solution. You want to just process data. Sometimes it's just doing some mapping which allows you to run everything in parallel. But just imagine that you are trying to put somewhere into the structure. In my case, I was using array list all the time. Did you notice that? That in all my tests, I used just a plain array list without any additional synchronization. Now, in case reactive streams are running like in parallel, you have to implement, like on next can run in parallel, you have to take care and provide additional data structure which will complicate your business logic. And reactive streams are created for simplifying your solution in order to make your life easier, not harder. That's why they say that invocation of on next couldn't happen in parallel or simultaneous. And the most important is you are right. Just imagine that you are running on next and then you are running in parallel on complete. How you should react? Just imagine that one operation is running at the point in time and now you have to do a cleanup because basically on complete or on error is a terminal operation, so it means that you could clean up all resources related to your subscriber if you're writing to, for example, WebSocket or to a network socket. Just imagine that you are still writing something into your WebSocket or network socket or TCP socket, that now at the same time you are trying to close this socket. So you have to put additional care in order to not close your socket before the previous operation completed. That's why it's much simpler to state in specification that everything should be serialized. So the proper synchronization should be done on your subscriber in order to prevent all simultaneous invocation of all these methods. Does it make sense? Okay, but this is kind of put more responsibility on the implementers, as we will see. Then what specification says in additional, that request method should be called in non-blocking fashion. Why it says should be? Basically, you can call request method potentially from different threads, but one can be blocked because another is working at this particular point in time. It says should because you can block another thread, but it says should because you can do it better, basically. On the other hand, when you are going to look at the specification and specification related to cancel method invocation, you will see that cancel method invocation must be invoked in non-blocking fashion, because cancel is a signal to kind of free resources for your publisher, because your publisher could be a publisher from WebSocket. So cancellation means that you have to close WebSocket because subscriber just say that there is no kind of requirement to listen data from WebSocket anymore. But closing of WebSocket could be a long-running operation, just in case. It could be whatever other operation, but you don't have to block your subscriber because of long-running operation of your publisher. That's why every operation in cancel method should happen non-blockingly and asynchronously, right? Does it make sense? So this is basically 3 rules which we have to follow in order to start kind of improving our publisher. So let's go back to our code. And first of all, that we have to notice here is that we implemented absolutely non-concurrent protected implementation so far. And there is one problem, one big problem, that TCK doesn't verify multi-threading cases. We created publisher, and it passes all tested from TCK, as you can notice. There is all passed tested. Of course, there is a few untested cases. They are kind of specified or says that there is untested cases which we can't test, but in general, all others don't verify any multi-threading. And this is a problem. If you're going to create publisher, you can easily end up with such implementation like this, right? So now we have to write our own test in order to check that our implementation is not thread safe. So in order to check that our implementation is not thread safe, I prepared some multi-threading use case. Yeah, I have to rewrite this guy. Assertion, assert that. Third, that my collection is equal to this one. Exactly, contains exactly these elements. Yeah. And this test is really simple. What I'm doing here, I'm doing invocation of my subscription request from multiple threads. So it's for sure check that I have some multi-threading environment, I have some concurrency on my request method, and my publisher should provide proper implementation in order to prevent multi-threading and to deliver all 5,000 of elements to my subscriber. Do you see that? So the test is really simple. I have 5,000 of elements, and I kind of iteratively schedule a call to fork join pool in order to invoke request 1. So I get 5,000 of requests from different threads. Is it clear what's going on here? OK. So after all, I expect that this guy will be invoked in serialized way. This happens before. That's why I don't need any concurrent structure here. So everything should be fine. Now I need to run this test in order to figure out whether it works or not. And here we go. We received only 6 elements, but we expected much more. And this has not happened. So let's go back to our implementation and try to figure out what we can do in order to make it working. Any ideas? Your thoughts? What we can do? Right. The simplest solution is just to make this request method synchronized. Yeah, of course. Like specification says that we should make request method non-blocking, but we could not follow this rule. And of course, if you're making our request method synchronized, everything will be fine, but our thread will be blocked. This is another problem. We don't like when something is blocking, and especially reactive streams states that everything should be async and non-blocking, so we have to kind of avoid this. But this is one of the solutions which allows you to make a proper implementation of publisher. So what other solution we can do without using synchronized keyword? Any other ideas? What do we know from kind of concurrency, and in order to make our field synchronized for different threads, what kind of keywords do we know? Volatile, right. So let's make all of our fields volatile. Why not? Let's do some dummy steps in order to figure out what should be the correct solution, and let's run our test. But again, the same problem. We expected n elements, but we got fewer of them than expected. I have to put another test in order to check that, for example, my collection has particular size has size 5,000, so it will be much more clear how many elements we received afterwards. So it's clear that we expected 5,000, but we got 129. So it's not something we expected. Why? If you're going to look at the IDE just mark and warning us that we can't do any kind of increase of element if this, or the field, if this field is volatile or marked as volatile. Why? Do you know why? Any idea? Because in fact, this request could be rewritten as this. Like it could be rewritten, and this will be absolutely correct way for G to rewrite this like this. Basically, we get the first initial state, and then we try to add to initial state something new and write back to the field. That's what's happening under the hood when we are going to look into generated instructions for our GVM. And this is basically a point of racing, right? Because just imagine tens or thousands of threads just try to read the same field at the same time and then write back the same state. This is a problem. So how we can avoid this racing during the increasement of the field? Huh? Right. So the next step is just to try to use atomic everywhere. So I prepared a code snippet for that because I don't want to use that. I don't want to rewrite that all the time. So I created a code snippet here, which basically introduces to our environment all atomic field, right? Because this should be a correct solution. So now we are using canceled, we are read it from atomic long because this is a proper solution. Then we are using absolutely convenient way to atomically add n elements to our field. So this is absolutely correct way, get and add, which adds atomically something to our field, volatile field. Then we read that from our field. And yeah, we're doing almost the same operation, and we do decrease of the number of send element in absolutely thread-safe way, atomic way, right? Should it work right now? I want to run some voting. Who thinks that this solution will pass tests? Okay, 3 hands. Who don't think it won't happen? Okay, a few hands. Others just don't know, right? Okay, so in order to figure out, let's just run test and see whether it happened or not. It didn't happen, again. So what went wrong? In order to figure out what went wrong, I have to go back to the slides, because this is really tricky concurrency point and racing point. So this is basically our solution. Here we have a few important points. So the first one is current state of requested field. So we have requested field, and here is kind of indicator of how many elements are at this point in time. Then this is initial requested field, and this is number of initial requested that we read from requested. So this is here we are running atomic operation get and add, which means that we are going to add something to this field. So this indicator will be changed, and we will read the previous state, and this will be atomic one. So if we're going to, for example, just imagine that we got thread black. So this one, the first thread. Thread black is the first one, so he tries to add some few elements to our initial to our requested field. So we will observe here that our requested field changed to 5, and our initial requested is 0, which is true, because no one else has been working prior us. So it means that there is no concurrency at all, and we just, the first thread entering this request method. So we are bypassing this verification because we are the first, we have to do the work. And now just imagine that we started sending data. What does it mean? That once we almost finish it, it could appear that another thread from absolutely different point in time or point in your code tries to increase or add a few elements to your publisher, or request a few elements from your publisher in addition, right? It could happen. Now we have 2 threads, black one and red one. But everything should be fine if black one will continue to work, but just consider corner case. Just imagine that one thread just entered, and the black thread is exiting execution. So he is trying to decrease some number of elements, whether another is trying to increase some or add some few elements to requested field. So this is a point of racing now. So in good case, the black will be winner or faster thread. So he is a winner, he is the fastest. So he just decreased n elements, and it's clear here that the returned number from add and get will be 0, because we decreased 5 elements from add and get, which means that we are the fastest, and it's clear that once we decrease that number of elements, the requested is 0 as well. So it was before 5. Once the black is fastest, it will be 0. Since the red one is loser, it will read it will read the changed state after the racing afterwards, because there is guarantee from atomic long. So the initial requested for red will be 0. It will add a few more elements back to the state, and he will bypass this invocation and will start or will continue sending some data to our subscriber, right? Does it make sense? So everything should be good. However, the evilness point here is the following. Just imagine that the red one is much faster. He is a sprinter thread. So he will increase much faster. He will win the racing on the request field, on the atomic field. And he will increase or send few more elements to our request field. So now, at this point in time, for red requested is 10. For black requested will be the same. But here, since there is a racing, black will just decrease his 5 element. So this is clear. I decreased 5 element by black. But there is nothing more for black. And what happening next? Black is exiting the invocation because he just doing a decreasement of elements, and that's it. Red is exiting, sending, and now we have a hanged publisher. Is it clear what happened? And this is a real problem of racing, because we don't know when we have to continue our sending. So if you're going back to our source code, we will see that what can happen. This guy can return or current state of requested. And there is no verification that checks that current state of requested is 0, right? So what we have to do is absolutely transparent or clear that we have to do some validation like this. If current requested is equal to 0, then we have to just return, and that's it. Otherwise, we have to repeat. So repeat, which means go to line somewhat and repeat something, right? But unfortunately, we don't have go to keyword in Java. So what we can do about that? What patterns do we know to repeat something again and again? What? Absolutely. We can write while. And we can write while like this. While true, why not? Let's iterate forever, or not forever, until the all element will be sent, right? So what's happening here? Basically, we start in infinitive iteration, but this is not infinitive iteration. One thread just entered this execution, he started sending, but once he got to this point of racing, if there is 2 threads which is trying to decrease and increase the number of requested elements, one of those will win and another will lose. In case this black one, just continue the naming, in case black one will win the racing, it will safely exit because there is guarantee on happens before. So if he's fastest, he will do that action first, and these changes will be available for the thread which is doing that afterwards. So this guy, if the kind of current state is 0, this current state 0 will be the same for this guy as well. So which means the other will exit and this will continue execution. Otherwise, the previous one is faster and this one is loser. He will see that there is few more elements to deliver, so I have to do a work for another thread. So what we have to do right now, we have to say, okay, Once we have to do a work for another thread, we have to reset our index to 0 and repeat work. This pattern in concurrency and in concurrent and non-blocking data processing call it work stealing. Because basically there is a few threads which are trying to do some work, so they're trying to request some elements, but only one will be doing the work for all of them. So there is one who kind of doing work or steal work from others, and others just deliver the number of requested elements. Does it make sense? Is it clear how it works? Yeah? Any questions? Okay, so I assume there is no questions, so we have to just, yeah. Yeah. No, it's not. We still have serialized data delivering. It doesn't matter from which thread we got kind of a request or invocation from request, because it could happen from different thread. It doesn't matter for us. The only matter is that we have to deliver or invoke our subscriber in a serial way without any concurrency. And since we have this pattern work in progress, which is now written in a thread-safe way, we can protect that no threads will enter this execution. And by applying some while true loop or infinite loop, in addition to that, we can make sure that everything will be delivered without any request losing. That won't cause any problem, because for us, it doesn't matter which thread is delivering data. It won't block any thread, but it will just add a few more work for the thread which is working right now. Yes, questions? Not? Is it not clear? Yeah, we can discuss it afterwards if you had more question, like in depth. For others, is it clear? Somewhat? Okay. So the most important part is that the test is passing right now. I can rerun it for thousands of times, and it will be passing without any problem, because now we are using non-blocking way of data sending without any synchronize, and this way is absolutely thread safe. Okay? So now let's, in order to make sure that we haven't broken everything, we have to run the whole test suite. And now let's wait for good news. But something went wrong. There is a test which is running for a long time, and it will be running for a long, long time, believe me, which says, must not signal an error when pending above long max value. What does it mean for you? How it sounds to you? If you're going to look at the test itself and try to, yeah, of course we have to open source code. Pending bow, yeah. We will see that there is an initial request. So if you're going to API, we will see that the first value here in test API is the initial request. You will see that there is initial request, like we request integer max value, but then we request long max value in addition. So now let's try to do some math, and let's try to add integer max value to long max value. What we will get? What we will get? Any idea? So let me just open terminal. Huh? Yeah, basically, let me just run terminal in order to show you that. Integer, yeah, integer max value plus long, come on, long max value. And we will get this number. It's totally something that we don't want to get afterwards. So first of all, we expected to deliver integer max value elements, but afterwards we have to deliver minus something, thousand, billions, millions of elements. And yeah, unfortunately, publisher can't deliver and can't satisfy this requirement. So the problem here is that we have this atomic get and add. And in fact, if you're going to look at the internals of get and add, we will see that we just use compare and set. We just do plain math. And it's obviously that it can overflow. The more important part is that if you're going to look at the specification says that in case our publisher requested long max value or request above the long max value, we have to consider our subscription or request as unbounded, which means that we are absolutely free to just push data without any verification and retrievement to decrease number of requested elements. Because delivering of long max value or long max value elements will take about 292 years, about 300 years. And I'm absolutely sure that there is no production that lives longer than 1 month without restart. So we can just consider this subscription as an unbounded. And now we have to somehow implement the same algorithm, because here is clear we use infinitive loop. And this infinitive loop is designed for racing again. And there is absolutely atomic operation compare and set, which allows you to compare what was before or what you expected to see in the memory. And then you have to add the next value afterwards, which is absolutely atomic operation. So now we have to implement something similar, but with protection for overflow, right? So the simplest, as for me, is to just copy-paste this and implement the same by ourselves. So the same, we have to do absolutely the same do-while loop, and we have to use this atomic long, etc., but check that there is no overflow. Does it make sense? So I'm going to use some shortcut again, and I'm going to put this loop, this shortcut here. But in general, it's doing the same. Like if you're going to compare this guy versus our, we will see that we are reading the previous state from our requested field. The same happens here. Get and long volatile. This is basically the same. But it's an unsafe part. Atomic long just do the same under the hood. Like, yeah, it's read volatile field. It's the same. Then we have to compare that current initial requested isn't already equal to long max value. Because if it's equal, we don't have to do anything. We can't increase it more because we just would have to just rewrite it back to long max value. It means that we can safely return back from the loop because someone is iterating, the request is high enough, so we don't have to do any math so far. Then what we have to do, we have to try to increase the value on requested one. And in case our requested value is overflow, we have to just set this guy to long max value because it means that something plus the next requested value will overflow, which means that the maximum for long is long max value. And afterwards, we have to run the same compare and set on our requested in order to make this operation atomic. Otherwise, there is a racing. We will repeat it again and again and again until we win the racing. Yes? Is it clear how it works? Yeah, this is the same pattern. This is compare and set loop. It's called compare and set loop, and it's absolutely popular and the most popular pattern in concurrency, non-blocking concurrency. So please remember it if you want to build some non-blocking concurrent system. And that's basically it, what we have to do. Right now, if we are going to rerun this test, you will see that everything should be passed. Yay, it's passed. Great. So, any questions so far? No? All good? So then let's move forward. If you got any question, just don't hesitate to interrupt me and ask. But in general, that's basically all we have to do in order to make our implementation working. So let's do some short summary. First of all, we have to, if we want to build some efficient, multi-threading, concurrent implementation of our publisher or any other solution, use non-blocking memory and efficient memory access from concurrent atomic package in JDK, in standard JDK. Then, in order to avoid any kind of racing, there is most common pattern, kind of infinite loop plus something. In the first case, it's infinite loop plus work in progress, which allows us to prevent multiple threading trying to run the same action concurrently. An infinitive loop is used here to avoid racing, because one thread trying to adjust some value to request, and another try to decrease some number of element after delivering. In order to make it just repeating, someone who has to steal some work or kind of do work for others. So this is kind of call it work in progress pattern, and it allows us to make our implementation again non-blocking and pretty efficient. So we have to implement own get and add in order to avoid overflowing, and this is absolutely clear because default atomic long or atomic integer does not prevent and do not do any checking in order to prevent this overflowing. Finally, to summarize everything, it works in multi-threaded environment. It's much more complicated. Does it look like hardcore right now? Is it? Or is it simpler enough for you? I don't know. Yeah, it should be hardcore one. But yeah, it's a time to optimize something because reactive streams, it's about real performance and real hardcore and super fast data delivering. So what about optimizations? What kind of optimization we can apply to any solution? First of all, we can optimize field access. If you're going to Google and if you're trying to find some information on Stack Overflow, you can probably find some blog post on Stack Overflow related to field access. So it's a question: what is faster, field access or stack local access? And in fact, access to variable from your stack is one more produce less kind of instruction to your processor, which means it should be faster in case we got lots of identical requests. So we have to move access from field to our stack, and from stack it will be faster. And it could bring a few % of performance win for us. Then we have to decrease the number of atomic operations, because in fact it could be a little bit overwhelming because we have atomic integer on our index, atomic long on our requested field, and atomic boolean. Do we need the atomic access for atomic read and writes for all of them? I'm not sure. Yes, yeah, this is one of the options. Yeah, we will be back to that. What else? Number of produced objects. Have you ever cared about number of created objects? In fact, all Java is kind of language which doesn't have any ref counting, and it provides you with garbage collector, which automatically cleans all the reference for all object which is not used by your application. It simplifies your life, but it puts more responsibility on you to decrease the number of created objects, because if you create too many objects, your garbage collector will require to check more of them, more and more links, and do more work for you. And it takes time, it takes your processor, so the performance of your business logic will be taken, or the time from your business logic, CPU business logic, will be taken for doing some garbage cleaning. So do not provide too many objects, so we have to take a look how we can decrease the number of created objects. And finally, we can improve execution path. As you remember, I say that if someone requested long max value, the subscription could be considered as unbounded. So your publisher could simply send data until the end of the data stream. So it means that we can decrease the number of access to requested field because we don't have to check how many elements were requested, and we have to just send, and that's it. Yeah? Does it make sense? All right. So let's turn to our second demo, and let's try to optimize our implementation. So what do we have? Yeah, this is our publisher. We have a few atomic integers here. We have a few access to cancelled field, like there. We have a few reads from atomic long requested here, and we have one write back to this field. So any idea how we can simplify our implementation according to those points of simplification or optimization? And can we just optimize our solution without doing anything? What do you do in order to make sure that your solution is more faster than before? Right. We have to measure first. How we can measure something small in Java? Have you ever heard about GMH, Java Micro Benchmark? This is a proper solution. Today, with JDK 12, it's part of JDK itself, and it allows you to benchmark your Java with a proper kind of rerunning and optimizing everything because Java is too smart. There is just-in-time compiler, which after a few iterations and running of your code will optimize the produced bytecodes, will recompile everything. And the runtime at the beginning of application could be absolutely different from the runtime, which is runtime after a few working hours of your application. It could be super optimized. And that's why we have to run proper tool which emulates the same behaviors. And there is Java kind of Java micro benchmarks. You can take it from OpenJDK, like an external dependency if you're using JDK 9, 8, 10, or 11. Today it's a part of JDK or OpenJDK. Anyways, I'm using it as a part of an external dependencies. And here I provided a few useful tests. First of all, in order to make sure that my previous solution is slower than current one after optimization, I have to store the previous code. Here is the previous code. This is a class called unoptimized array publisher, and it's basically absolutely identical to what we have right now. Yeah? So it's just a copy-paste. If you're going to run GMH, you will see that the performance is absolutely same. And here is the benchmark. So what my benchmark does, it does a few iterations. Of course, for real benchmarking, you have to provide 10 of iteration in order to properly warm up your system. For us, it's fine, so we can put 5 here. We can put 5 here as well, like for real measurement. Here is the time for measuring. So you specify how long will take your measurement iteration. So let's put it to 1, just in case. And then you can specify some output, etc. What it does, what my test does, basically. So here I create 2 publishers from integer array. In order to produce less garbage, I just make this test, this array scoped for thread. And then I'm running absolutely the same verification for every, like for both of the implementation. One for optimized one, so I subscribe to my stream and expect that 1 million of elements happens for some period of time. And then I measure the same for unoptimized. In this way, we will compare 2 solutions, and we will see how far we improved our performance comparing to what we had before. Does it make sense? Great. So let's move forward. Let's move forward, and let's try, as I say, to optimize something. Yeah. Array publisher, here we go. So, do we need atomic boolean for cancel field? Let's take a look. We do just a few reads from this cancel field here. So we read that canceled is not true. Then we read that cancel is not true again. And there is no write to cancel field. So do we need atomic at all here? Because we have only one write here. And basically, it could be just a plain write, right? Yeah, we don't have atomic boolean at all here. It's absolutely enough to put volatile boolean here instead. Why volatile still? Because it's absolutely correct if you're going to call cancel from a different thread. It's absolutely fine. The only requirement is that our cancellation should be non-blocking, not should be must be non-blocking. So we have to take care that this is just set to true, and then we can safely read at some point in time that this field is true. So eventually we will stop sending data. This is important part. And specifications say, if you cancel, you have to expect that eventually your publisher stops sending data, because everything could be asynchronous, right? In this way, we decreased few more objects for our garbage collector. Especially if you create a publisher of a few elements, it will be huge performance burst. So we are going to rerun our performance test once we do a few kind of improvements. Any other things what we can improve afterwards? What else can we improve? Do we need to read requested? Do we need to run every time on every loop volatile read here? Can we read once at some point in time and then refresh state on every loop of our while? So let's just consider the execution. Oh, sorry. Let's just consider the execution path. We got the first request. We know for sure that only one thread will bypass this invocation, but we know that the thread that bypasses verification will have the same request as we initially requested. Like n will be equal to requested field, for example, here, or initial requested plus n. Yeah, it will. Yeah. Anyways, like the requested field will be equal to n at this point in time. We can just assume that we don't have any racing, so we can assume that requested will be equal to n, which means that n is up-to-date state for requested number of elements. Yeah? Does it make sense? So we basically can say, okay, let's at the first iteration follow and assume that this number of requested element is equal to n. But once we iterated, once we try to decrease the sent number of elements, and in case this sent number of elements is not equal to what we expected, we can put the current state or the current number of requested elements back to n. So it will be updated state. Does it make sense? So in this way, if there is a racing, and if there is another thread that requested a few more elements, we will observe that afterwards, and we will update our state after this verification. And we will go back that again. We will try to deliver a few more elements. And if we get back here again, if someone requested more, we will redo and redo and redo the same action. So let's first of all rerun the TCK, and we will see that all tests are still pathing, which means that we didn't break anything. Yeah, it works. So by doing that, we decreased, and yeah. Which one? Yeah, we have it. We still have it. I'm running this test at the same time. So by running the whole test suite, I'm running the test from TCK along with the, yeah, so I have all of them. So yeah, I can rerun it to make sure that it's proper one. Yeah, all good? So our implementation still works, but now what we got that we don't have to read from the requested field on every iteration. So it decreased on n elements and the n access to volatile field, which is a huge win. What else? Now the more complex questions. Now I would say the most complex question. Do we need atomic integer for our index field? Do we need it here? Let's try to analyze our code. Here there is a guarantee. Yeah, this is basically work in progress guard, which says that the only one worker can work at a time, at a moment in time, which means that only one thread has an access to while true loop, right? Only one thread can iterate here. This is a requirement from specifications that everything should be run in serialized way, which means that only one thread can iterate at a moment in time here. So if you're going to look at this access to index field, you will see that only one thread will increment this index field, will read this index field, will increment this index field, and so forth and so on. Now the question, do we need atomic integer here? No, we don't. Okay, so let's write it like here. Let's just start from simplest. The following question, do we need volatile here? No, we don't, because there is Java memory model which says if we got a proper read from the same field, from the same volatile field before we start doing anything with with our iteration, and in case there is other fields, but they don't have any racing on them, and afterward, after our iteration on all of those fields, we got a proper write on volatile field, the other thread which will try to access to this iteration afterward will get the up-to-date information from the read of this field. Yeah, this sounds a little bit complex, but yeah, I have a link to Java memory model to this point, which clearly states that if we don't have any racing on some non-volatile fields, but we have a proper read and write, then the same information for non-volatile field will be up to date for every thread. This is an important point, which allows us to just remove volatile, which allows us just remove atomic integer, and make this field as simplest as possible. This is an important point here. So now again, let's just try to rerun the same multi-threading test, which says, all good. We can go ahead, there's no problem. And now, if you're going to run our GMH benchmark, so here is my performance test, you will see a good increasement in performance. In good case, for proper test, you will see about from 20 to 30% of win in performance. So we can wait for 2 minutes, but in general, we are going to just swap it, kind of skip it a little bit, and we are going to focus on final optimizations. So can we do better from this point in time? Can we decrease a few more objects from our memory? Can we? Any idea? Can we remove this atomic long and try to make this as just plain volatile long without creating any objects? Have you ever heard about atomic long field updater? So if you're going to Google, like we can create static final atomic long field updater. This is basically the same atomic long. If you're going to look, it has absolutely the same number of methods. The only difference, it requires to provide an object which contains a particular field, which we have, volatile field, which we have to atomically update. This is an important part. Since every class in memory is just a part of the memory, and we know at the class law time that there is an offset for this field, there is an offset for that field, there is an offset for other fields, and this class won't be changed in case we use some class modification, but in case we don't, we can safely say that we want to have an atomic field long updater, which will be associated only with one class. And what we got afterward, we could name this quested. And we can create this atomic long field updater and say that we want to do atomic updates for a particular class. Yeah, I'm just writing some abstract code. And I know that the field, which is volatile field, which should be updated atomically, call it requested. So once I start using this requested field on particular object, which is created from particular class provided here, this kind of updater will know particular offset and will be able to provide all atomic operation without providing or creating additional object in memory. So now let me try to refactor this guy a little bit. So let me do this kind of refactoring. Yes, not pull member up, but yeah, I want to move. Where is that? Refactor, replay, not this. No, come on. I remember that this was there in line superclass. No. Pull member us, replace, not. Where is that? Huh? No, I need to make this class static and need to move this to refactor this guy a little bit, but I lose, I kind of miss. Okay, so let's do like this. Yeah, let's do it like this, and now I should see refactor. Where is that? Move. Do you see move? Okay, so let's do like this. Move, yeah, Here we go. Totally. And now I can do it like a static. Okay, now I can apply some refactoring and can say, yeah, make this static class, refactor the static. And now I can safely use this atomic long field updater. And now I can say that here is my subscription. And now it will say that, yeah, I'm referring to particular class. Do you see that? Now I'm using this atomic long field updater, which is associated with my static class, its static field. But now if ID is know to which field I'm referring, so it will refer to this field, which means that this requested field will do proper updates on this volatile in atomic way. So let me just quickly switch to proper final implementation with some proper, yeah, the same implementation, but yeah, a little bit more fixed, since here now I'm using requested and just provided the current object and that's it. And now let's go back to our tests. And as you can see, we got better performance for our optimized publisher. It's clear that there is a huge error, about like 15 in performance difference, which means that it could be 70, 75 or more. This one is more errored, but in any case, we can see that there is a better performance. If you're going to run more proper tests, we will see a higher number, but anyways, our optimization made some sense to our implementation, right? Okay. Final optimizations that we have to run here, let me quickly switch to almost final solution. Final steps that we have to run is kind of verification of slow or fast pass. As you can remember, I said that long max values means that we can just simply send without any verification. And this is basically fast pass, where I just iterating until the end of the stream, and that's it. I don't try to access to any requested field, etc., which means that performance should be much higher, because there is no any writes and reads from volatile field at all. The slow pass is absolutely the same, so nothing has changed here. Now the final point. Let's try to compare that. So let me split my idea like this, and let me go to Flux array. This is real kind of real publisher. I mean real publisher from Reactor core publisher. So this is part of the library. And now let's compare both of them. Ours one, and official one. So in general, everything is identical. We accept the array. We do some subscription first. So basically, our subscription is a little bit more simplified, since there is more optimization, possible optimization, but basically there is our array subscription, there is our. And now we have to look at array subscription and compare both subscription. So here we had our subscriber to which we had to send some elements. Here we have the same usage of volatile requested in order to avoid creation of additional objects. If you're going to look to RxJava 2, you can see that RxJava extends from atomic long. This is another way to decrease the number of objects. This is only because RxJava is built on top of Java 6, and in Java 6 there is no atomic long field updater so far. So this is a better way to just extend object, and it will get the same performance effect. What next? Here is request field. Basically, request field in Project Reactor is a little bit utilized, like simplified, because some verification are hidden inside utility methods, like verification that n less than 0. Then we have the same add and cap as ours one. So if you're going to look, this is the same infinite loop over for loop for their case, which does do compare and set on some particular instance. And here is the same verification that we didn't get any overflow, the same as ours one. Do you see that? Yeah, it's absolutely the same. And finally, afterwards, if you're going to look at the main path, which means that this is work in progress with atomic sum with thread safety, then once the thread got to this point, it had to figure out whether it's fast pass in case someone requested long max value or slow pass. And slow pass will be absolutely the same as ours one. So here is, again, infinite loop over 4. In our case, it's absolutely more clear while true loop, but it doesn't matter for compiler, like for runtime, which way we are writing our kind of cycle. Then the same method delivery is the same null verification, etc. But over while, this is only different. Afterwards, the same check-in and the same kind of more advanced, kind of more optimized way to decrease requested number of elements. So our implementation is absolutely the same. And now you learned all the patterns, all possible non-blocking and concurrent technique, and now you should be able to read this crazy code, because you know why it was written like this. So let's do final conclusion, almost final conclusion. First of all, always do JMH. It's important to figure out whether something is better. First of all, you have to measure whether something is better. Read Java memory model. Java memory model sometimes says where it's enough to just use one atomic read instead of creating too many atomic fields. So in our case, it's absolutely clear that access to our index will be only done by one thread. So you don't have to provide this field kind of volatile or atomic, because there is guarantee from other volatile read and get, which will absolutely during to this link, during to Java memory model, will guarantee that all updates to non-atomic field will be visible to other threads because of volatile read and write from here. To save the world, reduce number of produced trash. This is important in real life and in every application. So create fewer number of objects, and you will get less stop the world, which happens in your Java application. Store everything in the stack. You can, again, preserve a few. You can do less CPU kind of operations or instruction. Again, this is a link to discussion, kind of thread local stack access versus instance access. But again, you can win from 2 to 3% of your performance, which is important for high-performance solution. And carefully learn specification, because it says that if long max value, you can just push. This is a simple one. All right, so let's do the final summary. We successfully optimized our solution. Our code is equal to Project Reactor, and now we are almost authors of Reactive Library. Pattern that we used: work in progress, infinite loop for work stealing and for doing proper increasement of requested number of elements. Fast pass versus slow pass in order to decide which kind of optimization depends on the requested number we have to do. And atomics long field or integer field updater in order to decrease the number of trash for garbage collector. Finally, for part 1, don't afraid to implement it, just read specification. Everything for performance. So if you're going to look at the reactive libraries like RxJava or Project Reactor, you will see the same patterns. All of them are done for high performance, but again, that's fine, and you know all the patterns used so far. TCK, if you want to check that your publisher is correct, and wash your hand after Govna code. Like from Russian, it's don't write. Yeah, it's clear for Polish audience as well. So don't afraid to write it, but wash your hand once you wrote really complex and shitty code. That's it. So this is the first part. Let's do 5-minute break, and then we will have the final implementation of the whole library, let's call it, and you will be able to go to the party. It will take 30 minutes, but yeah. Let's take some break, coffee if you have any questions, or we can just continue. Do you want to continue without any break? Okay, let's do a 5-minute break and continue.